So, okay, I'd like to talk about like Sperner field, Sperner lemma, and actually I came across this reading a graph textbook, and so Sperner's lemma, it is really nice. And then I went online and I see there's several videos talking about Sperner's lemma already. But I see that all of them didn't give proof for the higher dimensional case, so I just want to fill the gap there. And actually, basically, my proof here is following a lecture notes by Jacob Frost, from MIT. So, and Sperner's is actually this is a result from 1928. And this is a very kind of neat result, turns out a very simple proof. And I will state the lemma right afterward, but the consequence is it gave a very elegant proof for this so-called Brouwer's fixed theorem, fixed point theorem. It's a very famous theorem that basically, if we consider a n-dimensional balls, I can only draw 3D here. So n-dimensional balls, and if we consider any function mapping from this n-dimensional ball to itself, so draw map to this another n-dimensional ball. So for this function, there would be a fixed point. So namely that for some point here, after the mapping, it will map back to the same point. Okay, maybe I don't want to erase that. So ND, this is 2D. For ND, I will have I don't know how to draw that, but in general, I will have n vertices and n plus 1 vertices. Let me label from 0, 1 to, let's say, up to n. And so for the 2D case here, so I have 3 vertices here. And now the Sperner's lemma is basically considering the division of this subdivision of this n-dimensional simplex. In the 2D case, would be we'll divide this triangle into subtriangles, like this, let's say. And actually, this division can be kind of arbitrary shape. Here, I just make it kind of regular, but that's fine. And we will try to label all the vertices of these subtriangles with labels from 0 to 2, 0, 1, 2. So basically, for Andy, we'll try to label with 0, 1, 2 up to n. So I mean, I don't know how to draw it. This is kind of difficult, though. So we'll split into kind of subvertices. Maybe I just draw one. So that there will be each of them will be simplexes basically. I'm going to split this big simplex. Okay, 1 minute this simplex divide into simplexes. And I try to label each of the vertices of these simplexes. So back to 2D case, and the labels I have will be just n plus 1, so many different labels. So in 2D case, I would just have labels 0, 1, 2, and a proper labeling would be the following. For the vertices, I need to have different labels. Basically, maybe I put 0, 1, 2 here. And for the edge here, I can only include labels that is excluding. Basically, I can only include labels excluding the the label of the opposite vertex here. So basically, I cannot include 2 here. I can have like 1, 0, 1, let's say. And similarly for this one, I have to exclude 0 here at the opposite. I need to exclude this guy. I can have like 1, 2, 1 here, let's say. And for this one, I need to ignore this one. I mean, exclude this one here. So I can have, let's say, 0, 2, 0, something like that. And I need to also label something inside here. Maybe I can label like 2, 1, 0, let's say. And that's it, basically. Okay, we can basically the 2 rules here will be like the first one, we have the vertices of the large simplex have distinct labels. So 0, 1, and up to n here. So, and also like I will have the outside vertices. So basically the vertices kind of like fall on these edges. I mean, the n-dimensional case will be like the vertices like fall on the face of the original simplex. Simplex, or maybe I say large simplex. Cannot be labeled, cannot have the same label as the opposite vertex of the large simplex. So I hope this make it clear. So here I join this. This is not really anti-case. Like for anti-case, like the face here should have like n-1 dimension and have n vertices. But let's say this is really a 3D case. So, but for the 3D case here, so for this, let's just also be precise for the 3D case here, and the vertices of this large simplex will also be distinct, have distinct labels. And for the outside vertices, for example, for this face here, 0, 1, 2, the vertices like fall on this face, I cannot have label of this opposite vertex of the large simplex. So like this one, this vertex like can only have label 0, 1, 2, but cannot have label 3 here. So I hope this is clear, like the setup. So then basically the Sperner's lemma is saying that, okay, given these 2 rules here, I will have a distinct simplex. Oh, sorry. I mean, I have a simplex that's subsimplexes. Okay. I'll have one of the subsimplex have distinct labels. So in other words, in the 2D cases that like I will have, for example, like this simplex here, we have labels like 0, 1, and 2, right? So all of the labels will be distinct. And also like in the 3D case, I will have like a simplex here somehow inside or outside that will have like vertices I have labels 0, 1, 2, and 3. All of the labels will be distinct. So let me write down. If this is true, then there exists a subsimplest with distinct labels. And actually, we will show something stronger. I think maybe the lemma itself is stronger, but usually it will put it this way. The stronger statement is basically the number of subsimplexes with distinct labels is odd. So we have odd number of these distinct labels. So of course, because it's odd, it cannot be 0. So therefore, there must exist a subsimplex with distinct labels. So this is basically the Sperner's lemma. So now we will try to prove that. So the idea is to use use induction. So we'll start with like 2D case. Actually, we can say like the 1D case will be something like just considering a line. Okay, 1D case. We have a trivial 1D case is basically have a line, and we have a basically in this case rule number 2 doesn't mean anything, but rule number 1 is like I will have vertices like has to have label 0 and 1 here. And then if we consider the subsimplest with distinct label will be like if I have segment here, let's say I have segment here, I have label 1, 0, 1, and then the segment that have distinct labels will be like this one and this one and this one, right? And the number of segments, or number in this case is like, number of segments here have distinct labels will be equal to 3. So that's exactly satisfy this one here. So, and we can also look at this example here. So let's say, let's count the number of triangles here with distinct labels. Let me use another color. So I have this 0, 0, 0, 0, 1, this one does not have distinct labels. This one 0, 1, 2 have a distinct labels here. 0, 1, 2 have distinct labels here, right? And I also have the 0, 1, 2 here, and 0, 1, 2 here. And let's say, I also have 0, 1, 2 here. Is that all? I think, yeah, I think this is, oh, wait, I still have 0, 1, 2 here. And my 0, 1, 2 here. Yeah, I think that's all. Yeah, that's, yeah, that's basically all the triangles with distinct labels, and that's you can count as 1, 2, 3, 4, 5. Oh, okay, that must be something. Okay, 1, 2, 3, 4, 5, 6, 7. Yeah, that's correct. So I have 7 of them. Again, that's like an odd number of them. So for 3-dimensional, this is very hard to draw. I'm not trying to make an example. Now, so we can show it now. And for 1D case, and it's apparent for the 1D case, it will hold like, basically, if you consider 1D case here, I will start with like one segment have distinct label if I don't have any additional vertex here. So if I have had one vertex here, I have one vertex here, I can put a 1 here. It doesn't change the number of segments to have distinct labels. I still have one segment to have distinct labels. Now here I can, if I add one more vertex, I say here, I can put 1 or 0 here. If I put, actually this doesn't do anything for this one. Maybe I will consider this one. So here I do 1. Okay, let's do this anyway. If I put 1 or 0 here, the number of segments will still the same. If I put 1 here, I still have one segment here have distinct labels. Now, if I for this one here, if I put 1 here, it doesn't change anything. But if I put 0 here, I will have like 2 more segments have distinct labels. But of course, I each time if I have a segment that, for example, like have the same labels on both ends, if I put the vertex in the middle of this segment, either my label is the same as the other labels. If that's the case, I won't add any new segments to have distinct labels. But if I have put a labels different from the 2 ends here, if I put 0 here, I will add 2 more segments to have distinct labels. Therefore, each time I will either add 0 or like 2 more segments with distinct labels. And I start with 1, so therefore it will always be odd. Okay, that's the case for like 1D case. Now for 2D case, it's not actually trivial. So what we will consider is the following. We will consider among all these triangles here, or like sub-triangles or subsimplices here, we'll try to count the number of edges, number of C01 edges. C01, it's not 0, 0, C01 edges. And for example, like this one here, for this triangle here, has 1 C01 edges, 1 C01 edge. And then for this simplex here, it has another, actually 2 C01 edge, 2 C01 edges. And note that for this one here, this C01 edges like is shared about among these 2 simplexes, right? So therefore we will count twice actually, because we're basically counting like the total number of C01 edges of all subsimplexes, so subtriangles. So therefore, like for this one, we will have, even I have like 1 C01 edge is shared among these 2 subsimplexes. So therefore, we will count twice. On the other hand, for example, if I consider like this C01 edge here, so it will be only be contained in this subtriangle. So therefore, like it will only count once. So let me say the number of this boundary edge here. So let me call it, use the same notation of the nodes. So let me denote x, let x be number of C01 edge. Or actually, maybe I can just skip this edge here. This C01, okay, maybe I draw like this. C01 edge, so this is like an edge and C01. Number of C01 edge, number of outside C01 edge. So for example, this one, the green one here is an outside C01 edge, this number of outside C01 edge. And let's say this is equal to x. Okay, let x be a number of outside C01 edge. So let x be x. And let y be the number of inside C01 edge. So for example, this is the yellow one here. This is an inside C01 edge. And this green one here is the outside 0, 1 edge. So therefore the total number of 0, 1 edge of all subtriangles is equal to x plus 2y, right? Because like for the inside edges, like for the yellow one here, I need to count twice because it's shared by two triangles, subtriangles. Now but then we have another way to count all these like 0, 1 edges, right? The other way is like we basically just count all the different type of subtriangles. So note that like for subtriangles, I can either have this 0, 1 edge. If I have, let's say I have 0, 1, of course I need to have 0, 1. And for the first vertices here, I can have a distinct vertex. Let's say if I have 2 here, then I will only have one 0, 1 edge, right? In this case, I have one of these 0, 1 edge here. Number is equal to 1. So, and if I have one 0, 1 edge here, if the remaining vertex, if I have like either 1 or 0, in this case, I will have two 0, 1 edges, right? So in this case, I have 2 here. And note that I cannot have a third case. It's impossible to have like 3 0, 1 edges like for any labeling of a triangle. So, and let's say this is a type 1 case. This is a type 2 case. And type 1 case is the number of distinct triangles. And let's say this number we call it R. So R will be the number of triangle with, or actually maybe I can write more succinctly, number of this 0, 1, 2 triangle, right? Number of distinct triangle with distinct labels, and let S be the triangle either this or this. So this type 2 triangle with like the remaining vertex we have labeled either 0 or 1. So in this case, so we can count that the total number, again, count the total number of 0, 1 edges of all subtriangles. In this case, will be just equal to R plus 2S, right? Because for the first case here, I will have only one 0, 1 edge for triangle with all distinct edges. And the second case, I will have like 2 0, 1 edges. Now, these two will be equal. And now if we look at that, because first off, this is even, why I have 2 plus y, this is even. For x, I will claim that x is odd. X is odd because like the number of outside 0 edges is basically we are considering like how many 0, 1 edges on this edge here, right? Because this is the only edge of the large triangle that can have 0, 1 edge, right? And this is exactly identical to the 1D case here. This is exactly equal to this 1D case here, right? That's basically, for the 1D case, we already show that like the number of like 0, 1 segment here will be odd for the 1D case. So therefore, like x here is odd. So we know that this is odd. So therefore, like this number is odd. And therefore, like I have 2s here, therefore R must be odd. And what's R again? R is the number of distinct triangle, right? So this basically show the 2D case. Okay, now let's consider the ND case. So we're going to prove the n-dimensional case using induction. But before, like I guess I need to be clear again. In ND case, what is a simplest and subsimplest is like. So for the n-dimensional case, for example, let's just look at this. Is actually this is really a 3D case. The simplest will have like 4 vertices, and a also subsimplest will have 4 vertices as well. And when we consider a face of this 3D case, will be just a 2D triangle or a 2D simplest that with like 3 vertices. So therefore, like in ND case, it's really like a simplest there. You have one node will be kind of connecting to like n other nodes. So therefore, that will be total n plus 1 vertices. And if we consider a n minus 1 faces, n minus 1D phase in this ND case will be basically a n minus 1 dimensional simplest. So in that case, we'll have like 1 vertex will be connecting to n minus 1 vertices. So and for the ND case, okay, I guess let's see. I need to erase something as well. So erase, but erase here, this one here. So for the ND case, we'll kind of similar to in the 2D case, we'll do some counting. So we'll consider the total number of, in the 2D case, we'll consider the total number of CL1 edges, right? That's, or like you can think of the edge in 2D case is like also phase, it's a 1D phase. And in this ND case, we are considering like number of n minus 1D phases that have distinct vertices and precisely the vertices are 0, 1, 2 up to n minus 1. So we want to count all the number of, this is a n minus 1D phases. Let me give a name for this one. It's becoming really mouthful. Let me just call this thing like D phase. So I want to count the total number of D phases among the simplexes in all simplexes. Or subsimplexes. Okay, maybe it's easier to first look at the 3D case. So what one mean that is that like I want to count all the 2D phase. The 2D phase is like with vertices 0, 1, and 2. And I want to count the number of these 0, 1, 2 phases among all the subsimplexes. And in this case, the simplexes will be a tetrahedra, and we want to count all these tetrahedra. And sorry, all the D phases in this tetrahedra, 0, 1, 2 phases in this tetrahedra. And if we want to go further, extend to 4D case, let me just give one more example, just make sure I'm clear myself. So in the 4D case, in that case, we'll going to count these D faces now become like 0, 1, 2, 3 tetrahedron. And we want to count the total number of these D faces in all subsimplexes. Now, in the simplexes, now we'll have, in the 4D case, we'll have 5 vertices. So, and this, for example, like for this D face here, it can connect to one more vertex to create a subsimplex. So this one more vertex can have label like 0, 1, 2, 3, or 4, something like. And okay, hopefully I'm clear now. So, and now go back to here. This is what we're trying to count. And again, I will do something very similar to the 2D case. So let's consider when we will have these D phases. Of course, for subsimplexes have a D phases, we will basically have the subsimplex have all these vertices, say one of the D phase have vertices, say 0, 1, 2, up to n-1. This, I don't know how to draw that. And this is one of these D phase. Now it can connect to, this is a D phase here, D phase. It can connect to one more vertex to create that subsimplex. And the remaining vertex can either have two cases. It can have the remaining label n. So in that case, that subsimplex will have only one D phase, right? So we have this one D phase here, and that's only one D phase. And also, like for this simplex here, we'll have all the distinct labels. And let's say the number of such simplexes have all distinct labels will be equal to R, just like in this case here, in the 2D case. Now maybe I can erase maybe somewhere here. So maybe I write it as R. Now the number R is basically a number of simplexes have all distinct vertices, 0, 1, 2, blah, 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 up to n. And another case that a simplex will contain a D phase will be, first it contains a D phase. Now for the remaining vertex here, I don't have label n, but instead I have labels from 0 up to n-1. So let's say I have a label 0 here. Now in this case, we'll exactly have two D phases because I have the other D phase will be like kind of replace this original 0 vertex with this new 0 vertex. So like for this D phase here, for all the remaining vertices will connect to this 0 vertices, the remaining vertex instead. So this is the other D phase. So in this case, I will have like two D phases, right? And let's say like we'll count the number of all these simplexes have the remaining vertices is 0, 1, 2, up to n-1 as S. So again, maybe I can replace here. Actually, maybe I can use a different color, then it's more apparent what we change. So what we said is like we can actually keep the same kind of notation as before, but now we extend to higher dimensions. R is basically the number of simplexes with completely distinct vertices. So we have like 0, 1, 2, up to n. All vertices have distinct labels. And S is the number of simplexes have almost distinct labels. So basically, I have a D phase that have vertices like 0, 1, 2, up to n-1, and then have the remaining vertex that have either 0 or 1 or n-1 or up to n-1. It can be the remaining vertex is 0, 1, 2, and so on up to n-1. And all these possible simplexes, we add them together, the number will be equal to S. And for this case, each of them will have like 2 D phases, right? That's the phases we want to count. Again, D phase is the n-1 dimensional phases with distinct vertices, and the labels are precisely 0, 1, 2, up to n-1. And again, like in the 1D case, like in the 2D case, we can count it differently. Yeah? We can count directly these D phases in the simplex here. So if we count the number of D phases directly, we say the number of outside D phases be X. So basically the D phases outside. So for example, in this 2D case, like 0, 1, I will have like D phases will have like vertex label 0, 1, and 2. So, and let's say I have a phase here, I have 0, 1, and 2, and this will be an outside D phase. So for this phase of the large simplex here, I can have also like count the number of inside D phases. I count, I say the numbers for these inside D phases will have a total number of these inside D phases is equal to Y. Now then, I will have the exactly same conclusion as the 2D case here. Will be the total number of D phases of all subsimplexes will be equal to either R plus 2S or equal to X plus 2Y, because like in the 2D case here, if when I'm counting D phases, the interior D phases, they will be shared among 2 subsimplexes. So therefore, I need to double count that. So therefore, I will have like 2Y here. And for the outside one, I will just count it once. So I have X plus 2Y. And I'm also like, as we discussed previously, so for like, when we have this type 1 all distinct, simplexes for all distinct labels, we'll only have 1 D phase. And on the other hand, for this type 2, if we have one of the remaining labels is not distinct, then we have 2 D phases. So if we need to double count that. So we have the same equation, X plus 2Y is equal to R plus 2S. Now, like the 2D case, we'll argue that X is odd. So therefore, R is odd. That will complete our proof. Okay, now For x, the number of D phases, the number of outside D phases. In this case, first of all, I realized that these outside D phases can only fall on the face of the large simplex with vertices 0, 1, 2, up to n-1, right? For example, like in this 3D case here, the D phase that eventually is like the vertex, the triangle with like vertices 0, 1, 2, can only fall in the face of this large simplex or large tetrahedron with like labeled 0, 1, and 2, because that's the definition of proper labels, right? Otherwise, the labeling is not proper. Like I cannot have vertices here. Like if this my D phase here is a if I put in, for example, like on this phase here, I have 0, 1, 2 here, then I have this 1 here is improper labels here. So therefore, like it can only fall in this phase here. And I cannot go backward. I want to, oh, that's, okay, now I can. So, and the number of D phases in this case would be just the number of simplex with all distinct labels. That is actually, in this case, just fall back to the lower dimensional case. So it's like we fall back to the n-1 dimensional case, and we want to know like what's the number of simplexes with all distinct labels. That's exactly by Sperner's lemma. If our labeling is proper, then this number will be odd. So therefore, like by induction, if we assume that like everything is true up to n-1 dimension, then this number is odd, so therefore x is odd. There's a slight caveat here that I guess like this statement may not be sufficient because my D phase here, I want to make sure that like the phase of this large simplex also have like proper labeling. So for example, if I have somehow I have vertices here, like I have 2 here, it won't be a proper labels. So therefore, I should also make sure that like when I state this statement here, probably I should add a fine pin here that like I should also make sure that like phases of the large simplex is also properly labeled. And this should be kind of like true recursively. So I can go back, like for example, start with n dimensions. If look at all the phase of the m, so we satisfy the first 2 statements here basically, and then I consider this n dimensions. I look at all the n-1 dimensional phases. They should be properly labeled by the definition here. And if I look at the n-1 dimensions phases there, then I can look at the n-2 dimension phases of this n-1 dimension phase, and then this n-2 dimensional phases to satisfy this here. So and so on and so forth. So now we are done with Sperner's lemma. We'll just give a quick proof of the Brouwer's fixed point theorem. So let me, I think I can erase most of the stuff here. So for For Bowers fixed form theorem, the original statement is that like we're going to consider mapping from the n-dimensional ball to the n-dimensional ball itself. But we can essentially consider the n-dimensional simplex instead, because like any n-dimensional simplex will be homomorphic, homeomorphous to the n-dimensional ball. Or you can think of like if you're not sure what homomorphism means, it's just that, for example, if I consider like in the Bowers theorem, like we consider all the condition mapping, right? So let's say the mapping is F here. I can think of like, okay, instead of like considering this n-dimensional ball, we'll consider the, maybe I don't need to draw like the axis here. Oh, okay, maybe I draw, yeah, it's actually harder to draw the axis. So let's ignore the axis here. So we can consider the simplex instead. So n-dimensional simplex, maybe I draw like this, dotted line here. So I can consider like a linear, that would be a linear mapping, not linear, continuous mapping from the n-dimensional ball to the n-dimensional vertex. That this is like this linear mapping, not linear, continuous mapping will have an inverse. So it's a one-to-one mapping. And so, and that's what we mean by homomorphism. So we know that that's like invertible one-to-one mapping from the n-dipole to the tetrahedron, or like to the n-dimensional simplex. So then in this case, like if there's a fixed point, if we can show that like there's a fixed point for any function, let's say any function f tilde from the tetrahedron to for this simplex to this simplex, there's a fixed point for any mapping for f tilde, then for f can be considered just as a mapping of, so in this case, f is really equal to g f tilde g, maybe I should write the other way around, is equal to g f tilde g inverse way. So now if I know that for any mapping in f tilde, there will be like a fixed point, then there will be a fixed point for f as well. So more precisely, let's say there's a fixed point here, like y. I know this is a fixed point such that like f tilde y is equal to y. Then I basically, the fixed point for f will be like g inverse y, right? So basically I will have like f g inverse y should be just equal to g inverse f tilde y, and that is equal to y, right? G inverse y, that's, yeah, and therefore this is a fixed point for f. So therefore, we for Bowers fixed point theorem, we can really just show that it's true for tetrahedron. Sorry, for simplex, right? So what again, we're going to do is look at this simplex here. I'm just going to look at for any mapping from this simplex to itself. We want to show that there's a fixed point, and we will basically for any point inside the simplex, we are going to use this so-called like barycentric coordinate. So namely, like for any points inside a simplex, let's say I have this label 0, 1, 2, 3 and for any point inside this simplex can be think of like a linear combination of coordinates of these points here. So let's say x will be equal to a0 x0 plus a1 x1 plus a2 x2 plus a3 x3, where this weight here will be normalized. So a0, a1, a2, a3 will be larger than or equal to 0, and sum over ai is equal to 1. So any points inside the simplex can be just think of linear combination of these vertices. So then I will have a different coordinate system. Now we can think of any points will be replaced by this a0, a1, a2, a3, and so on. And also like I can have here honestly I want to okay, that's okay. Let me just keep the notation like this. And then after the mapping, I will have like fx, and I can convert that to this new coordinate system again. Like maybe I just write fx0, fx1, fx2, fx3. So it's like the barymetric coordinates for fx. Now what we will define some sets S0, S1, S2, S3 here as like a point is inside S1, let's say X is in S1 if A1 is bigger than or equal to Fx1. And similarly, I can define S0 and S2 and S3 in the same manner. And this is of course, it's a 3D example. And for n-dimensional, I can do exactly the same thing. Basically, I say like Si is equal to all the points, such that Ai is bigger than or equal to Fxi. So is after the mapping, the ith coordinate of the barymetric coordinates, according to barymetric coordinates, is not strictly, it's kind of like non-increasing. So first of all, I want to claim that like for any point in this simplex here, it will belong to one of these S at least. So I have like in n-dimensional case, I have S0, S1, and so on up to Sn, right? So because I have n+1 vertices, I can have this n+1 sets here. Any points I claim like it will belong to one of these, at least one of these S here. First of all, maybe it's easier to just look at the vertices here. So for the vertex, for example, this vertex 0 here, apparently it would belong to S0 because x at this coordinate here, according to the barymetric coordinate, at vertex 0 here, actually the coordinate will be just 1, 0, 0, 0, right? That basically like A0 equal to 1, and then the y is equal to 0, A1, A2 equal to A3 equal to 0. And so therefore, if you look at the A0 here, it's already maximum. It must be like bigger than equal to, because we cannot have actually also like A should not be bigger than equal to 1. So A0 is already maximized. It cannot, after the mapping, it cannot get smaller. Oh, sorry, it cannot get even bigger. So therefore, like I must have like A0 is bigger than equal to Fx0. So therefore, like it must be like inside S0. And similarly, I will have like this vertex 1 should belong to S1, and vertex 2 belong to S2, vertex 3 belong to S3. And for all the other points here, so as I claim that like X has to be all the other points X inside the simplex here has to belong to one of these S, at least one of these S, because if otherwise, that means that like I have AI is strictly smaller than Fxi for all I. And this is of course impossible because we have the constraint that the sum over AI is equal to 1, and also sum of Fxi. This is also like in barymetric coordinate, also it should be sum over 1. So if this is strictly bigger than, that means that this is strictly bigger than 1. So that therefore like it should not be a parametric coordinate. So therefore like for any points in the simplex, it has to be inside one of the S here. It can fall into more than one S, but it doesn't matter to us. We say like we'll just pick the S that will give us proper label. So first of all, like if we look at the vertices here, because they already belong to S0, S1, S2, and S3, and if we pick the label such that it belong to some S, in this case, belong to 0, 1, 2, 3, already like for the vertices, we are good. Like they all have distinct labels. They are good. Now, and for the phase here, like for example, for the phase, maybe this phase here, 0, 2, 3, for any point X on the phase, for it to have proper labels, it should not have the label 1 here. Now, if I consider coordinate of the phase here, like the parametric coordinate of a point on the phase here, the coordinate should have A1 equal to 0, right? So it's actually very easy to see because like this one is a linear combination of these 3 points here. The parametric coordinate is just saying that, okay, I have a linear combination of these 3 points. And that should have no contribution of X1 here. Otherwise, it will pull it out from this phase here. So therefore, like on this phase, A1 is already 0. So for S1, for the point to fall inside S1, we must have like Fx1 is less than equal to A1 is less than equal to 0. So this is only true when Fx1 is equal to 0 as well. So that means that it's true if like Fx1 is fall on the face as well. But like if it's fall on the face, what I want to say, like if it's also on this face here, I know that like that should have like some, it should not just belong to S1, it should belong to some other set like S0, S2, and S3 as well. It's basically by the same argument as what we have earlier. So if it's not the case, that means that like I will have Fx. Basically, I will have like here, I already have like Fx1 is equal to 0. If it's not inside like S0, S2, and S3, S0, S2, S3, I will have like Fx0 plus fx2 plus fx3. Write it better. Is strictly bigger than like a0 plus a2 plus a3. And this is actually equal to 1. So again, like this cannot be true. So therefore, like any point, even though f if really a point on the face like 0, 2, 3 map back to the face 0, 2, 3, I know that this will be, this point should also belong to one of these s instead. So therefore, I can also like always label it like not with s1, or not with label 1 with label like 0, 2, and 3, right? So by the similar token, basically for all the faces, I can create a proper label anyway. So I can create a label such that like the label a points belong to label. Basically, what the eventual outcome is like a point x belong to label si. That means that like I have ai, or like I should say like that's why I kind of thinking whether it's a good idea to, okay, it's okay. Like just it's although it's a little bit bad. So AI is basically equal to the ith coordinate of x is bigger than equal to fxi. So if x is labeled by I, then x is in Si, and also like I have AI is bigger than equal to fxi. And of course, as I mentioned, in the Sperner proof, Sperner's Lemma proof, I need to show that the proper label is it holds like for kind of recursively. So in the sense that if I consider just the face here, so the face here is a proper label. I want to make sure the edge is also proper label as well. That means that like for this edge here, for the CO2 edge, I want to make sure that it doesn't have it shouldn't labels to like anything other than CO or 2. But of course, like for the CO2 edge here, what's the barymetric coordinate for the any point on the CO2 edge will be something like we'll have non-zero for A0, but for 1 and 3 will be just equal to 0, right? So I have 1 and 3 equal to 0, A2, 0. So basically A1 and A3 equal to 0. So again, like we can, by the same token, it's possible that this one belong to, let's say, a point here belong to S1 or S3. In that case, it's basically mapping on the same edge here. So the F upon here map in the same edge here. But again, like by the same token that we argued earlier, if that happened, still we can find another set 0 or 2 such that like that point should also belong to S0 or S2. In that case, we should label it with S0 or S2 instead. So again, we can always find a proper label, basically. We can find a proper label to label all points in X, basically, such that like X is labeled by I. If X is Si, that means that the barymetric coordinate of X, the ith component, is bigger than fxi. And also, okay, because I erased all this here. I guess I better write it out. Can always find proper label according to Sperner's lemma. And also the label have this meaning, like have this meaning here. For all x inside simplest. Now, of course, like by Sperner's lemma, then I can subdivide whatever, like I can create a subdivision of this simplest into final simplexes. And I know that would be like there exists a simplest, subsimplest with all distinct labels. And also like my division can make arbitrary fine. So I can eventually get to a really, really, really tiny simplexes that have all distinct vertices, like 0, 1, up to n. And they almost converge to 1 point there. Actually, I can make it converge to 1 point eventually. Therefore, like essentially, that point I can find 1 point that simplest have like that extremely tiny simplest with like all distinct vertices. And remember that what's these labels mean? And these labels means that like when that point is with that label, that means that that point will be inside SI, or the ith coordinate of x will be larger than equal to fxi. So if I have this point essentially is inside for all the SI there, that means that like for all I have AI is bigger than equal to fxi. And this can only be true if AI is equal to fxi, right? Because all this is normalized because I have the constraint that sum of AI equal to 1 and sum of fxi is equal to 1. And of course, if AI is equal to xi, it just means that like x is equal to fx. So therefore, like this is the proof for the Brouwer's fixed form theorem using Sperner's lemma. Another interesting application of the Sperner's lemma is rental allocation. Actually, before that, let's consider a simple problem, or actually a similar problem like cake allocation. Let's say I have a cake, and then we're going to split that among several friends, and we want to see like how we're going to cut this, so like each of the friends have the what they want. So let's say we just, for simplicity, assume that we only have 3 friends there. Let's say just A, B, and C. And now let's say we consider in 2D case, we have like a triangle with like 3 vertices. And again, if we use the barycentric, okay, I'm sorry, I guess earlier we said barymetric, it should be barycentric coordinate. So we can think of like any points inside this triangle with the barycentric coordinates as a way of splitting the cake. Because remember, the coordinate will be like A0, A1, and A2. So where that sum will be equal to 1, right? So that will be basically how we split the cakes, like any points there. And then like what we are going to do is we'll first, let's say we'll just split this triangle into subtriangles. And let's say for each of the subtriangles, we assign a kind of A, B, and C to the vertices. So where like if I have a vertex A, that means that like for that allocation, Alice have the priority to pick the choice of his cakes, of her cake. And let's say I put A, B, C, and then to be fair, let's say this is A here, this is B here, this is C here, and B, A, and so on and so forth. Basically, I assign this kind of the labels. Okay, this is a different labels. There's two sets of labels. I guess I have to be careful. One set of the labels, this is A, B, C, is the label of the is the basically the name, okay, or the what's that word? The initial of the friend that that have the priority to pick the cake, and then like, so of course it will be meaningless if I ask the friends, okay, let's for each of these vertices, let's pick the choice here, and then we'll kind of decide. That would be like too many questions, right? What we want is that we want to use the Sperner's lemma, and we know from the Sperner's lemma that like we don't need to fill the interior of the triangle for the labels. We only need to fill the exterior, and then like we know that there's an allocation in the interior that's for small triangles here. This one can be sufficiently small that like will have a distinct labels. Okay, here I only talk about the friends initial here. There's of course another labels is basically like the labels would be 0, 1, and 2. Basically, for example, like for this one, that's the allocation that like cake 0 will be like biggest piece. Actually, the entire piece is like have the fashion like that's basically low cut. Cake 0 is just equal to the original cake, and then cake 1 and cake 2 is nothing. For one, basically for the rest, like they are not getting anything. So for this choice, it's quite reasonable that like for this allocation, I would say like, and the rational person will pick, at least I assume that they're hungry, they will pick like cake 0. And then similarly here, let's say this is the allocation, like 0, 1, 0. So in this case, like anyone who is reasonable will pick cake 1. And this one is like 0, 0, 1, that anyone reasonable will pick cake 2. Now, then like we need to, and then like, okay. And then we need to look at the sign. So what was this? The sign labels here basically is like we will alternatively, iteratively ask like the friends B, C, and A, Bob, Alice, and Charlie, and to see what's the preference. Basically for this one here, the allocation should be something like I don't know, approximately should be I think this looks like something like point A and point 2 and 0. So for this allocation, so this is like going to ask like what was the preference of the cake. So depends on the cut. Maybe some of the friends would prefer like to the kind of like the boundary of the cake, right, with the crust or something, and maybe like someone is more preferring the interior. So for this one, I will basically ask Bob, what is his preference if the cut is like somewhere here? The first piece of cake says 80% of this part is cake 0, and then this part is cake 1, and cake 2 is nothing. And then it's likely that Bob will pick like cake 0, I guess. So maybe this is 0 here. And similarly, as we go down this one, this allocation will be like 0.6, 0.4, and 0. See something like if I make a cut somewhere here. Again, we'll ask the same question, like to this time it's not to Bob now. This is going to ask to Charlie. So if we have an allocation cut here, so this piece like cake 0 is here with about like 60% of the original cake, and then cake 1 is the about 40% of the rest, and then cake 2 is basically nothing. Ask him to pick like which cake he wants, like cake 0, cake 1, and cake 2. So most likely also like maybe I just like different labels, different colors. So this is 0, 0, and this is maybe it will pick 0 again. Of course, there's also a chance you want to pick 1 here. Maybe he liked I mean maybe this has a cherry here, and he preferred that the piece like with a cherry rather than like it's totally bland or something like that. So but anyway, like as you can see, like if all of these friends here are hungry, it's reasonable that they won't pick like empty cake. So therefore, like so along this edge here, because like that cake 2 is always just nothing. So the labels here should be either 0 or 1. And also like on this side, like because cake 1 will be nothing, so the labels here will be either 0 or 2. And then like here, cake 0 is nothing, so it's always 1 and 2. And immediately we see that this is a proper labeling. So therefore, like we know that there will be a interior triangle with distinct labels. So with 0, 1, and 2. And then like for that thing, then how we are going to allocate the cake, we'll take an average of that, right? So, or like we can of course make it very fine, but or like we can just make approximation. For example, like for this point here, maybe just get back. Let me use black again. So this is like A and B, right? So let's say eventually this is the triangle that have distinct labels. So in the sense like maybe this is like 0, and this is 1, and this is 2. So then how we're going to split the cake is basically we can get to the centroid. There's an allocation for the cake here at the centroid. So we'll split according to that one. So then most likely we'll split the cake. Maybe it looks like we will have a bigger piece for piece 2, and piece 1 and 0 will be more or less the same. So and then like we'll basically Charlie, as you can see, is prefer like 0. So Charlie will get the 0 piece here. This is for Charlie, and then like Alice is going to get the first piece. So this is for Alice, and Bob is going to get the second piece. So this is for Bob. So that's a cake allocation problem. And actually a modification of this problem, this went allocation problem went into a New York Times article, and this get more interesting because I probably it's a more realistic problem. Then if we consider like again like we can have some friends here, like maybe again Alice, Bob, and Charlie, and went to allocation. So when share a apartment and want to split different rooms. So Steve want to split the rent, and then they want to pick their rooms. So let's say I have again Alice, Bob, and Charlie, and let's say we also have room 1, 0, 1, and 2. Again, we can do the same thing, right? We can put a triangle here. So for each point in the triangle, we will have a rental allocation. Rental allocation that split the bill, and at the same time, like we can do the same thing as we split the triangle, and then like for each of the triangle, we can give priority for each of the friends here, like what's the priority of picking, okay, who have the priority to pick the room in that allocation. So for example, like for this point here, that have a particular allocation, Alice will have the priority to pick, like given this choice price allocation, which one she want to pick. But note that like if I going to use the barycentric coordinates again, there will have a problem here. As you can see, for the barycentric allocation, if I have room 0, 1, and 2 here, the one allocation here would be like 1, 0, 0. So that means that like Alice is going to pay for everything. I mean the entire bill for the apartment, and then or not Alice, or like I should say like room the one who stay in room 0 will pay for everything for the bill, and then those who stay in like room 1 and 2 doesn't need to pay anything. So in this case, for very logical, any logical person will pick like either 1 or 2, right? So and this one here, similar manner. Let's say this for this one, we'll have. Let me get back to other color. We'll have this one is have a price allocation of like 0, 1, 0, basically like, and the one who stay in bed room 1 is going to pay for everything. So in this case, anyone who is rational, I don't know who is going to be here, maybe let's say Alice, Bob, maybe this is a Bob, maybe, and this is Charlie, let's say, going to make the selection. So, and actually it's better to use black for the friends and then red for the selection here. So then in this case, anyone rational will pick either 1, 0, or 2, right? And similarly for this one here, let's say Charlie have a chance to pick, and this is the allocation is 0, 0, 1. So basically, the one who stay in room 2 now is going to pay for the entire apartment. So therefore, like those who is rational is going to pick like 0 or 1 for the room. Now how about the edges here? So for the edges here, let's say consider this edge here. For this edge here, for example, for this one here, the allocation will be something like will be something like 0.8, 0.2, and 0. So something like room number 1, who's the guy who's staying room number 1, number 0. Oh, sorry, number 0 will be paying 80% of the bill. The one who's staying in room number 1 will pay 20% of the bill. Those who stay in like room number 2 doesn't need to pay anything. So then, of course, you see like along this line, basically like it's always like those who pay staying in room number 2 doesn't need to pay anything. So we expect that like basically everyone will pick room number 2 here. And similarly for this one, everyone will essentially pick room number 1 here. And here, like anyone will pick room number 0 here, because along this line here, the rent allocation is like room number 0 doesn't cost anything. Now, you see like does have a slight problem in this allocation, because you see that like first of all, like it doesn't necessarily like fit into a proper labeling, because you see this is like I have 1, 2, 0, 2 here. I need to make sure like this is all 2 here, So I need to make sure this is either 1 or 0, basically. So, and essentially, like if you look at that, like if I want to have here, basically, if I want to, actually I cannot because here, if I want to have proper labeling, this has to be either 1 or 0, like to be logical. But if I pick 1, this will kind of make it not a proper labeling for this side here. If I pick 2, it won't make proper labeling for this side here. So in the original paper, this is actually, it's from a paper back in 1999 by Francis Su. And in his original paper, he suggests 2 possibilities. One, I think, is more complicated. It's like you were going to have build a dual simplex. So in the sense, we're going to map this simplex into a dual simplex such that there will be one correspondence of this subsimplex to the dual. And the vertex will be can map in a dual manner as well. And there we can find a proper labeling for that. This one actually I didn't go into detail, and I don't know exactly the detail how they're going to do it. But a easier solution, if we allow to have negative ones, then of course the easier solution will be simply we flip the problem here a little bit. Basically, like for this point here, instead I have 1 0 0 0, I have -1 0 0. So, but of course, if I have a problem like that, so that means that I will basically have all the input. I will just flip the allocation there. So for this one, I will have -a, -2, and 0. But of course, I need to make sure that for this to be a barycentric coordinate, I need to add up to 1. So that what we can do is we just add each point of the coordinate by 2/3, right? So if we add 2/3, that essentially the sum is added by 2. So then I have this original sum of the coordinates 1. So I flip the sign, I have -1, -1 plus 2, I will add back to 2. So that's good. So that what it means is therefore at this point, for example, at this point, I will have, instead of 0 0 1, I'll have 2/3, 2/3, and 2/3 -1, or this would be -1/3. So in this sense, the one who's staying in room 0 here will need to pay 2/3 of the 1. The one who staying in room 1 will pay 2/3 of the 1, and one who's staying room 2 will have some money back. Will back 1/3 of the 1 back. And then in that case, everyone will pick room number 2. So therefore, for this one, if I do that, flip the sign, so then I will instead have, in this case, everyone will pick room number 2. And here, anyone will pick room number 0. Anyone will pick room number 1. And also, along this side here, now the allocation, instead of point A, point 2, 0 will be minus point A, minus point 2. But so it's 2/3 minus point A, 2/3 minus point 2, and 2/3. So so anyway, it looks in any case, I will have the room number 2 will be always most expensive. It's equal to 2/3 of the entire bill, and the other one will be deducted by something there. So for any rational person, therefore, along this line here, oops. Along this line here, they should not pick the room number 2. So therefore, it should be either 0 or 1 along this side. And similarly, for this along this line here, room number 0 will cost like 2/3 of the entire bill, and for room number 0 or 1, oh sorry, room number 1 or 2, that will cost less than that. So then no one will pick like room number 0, so it'll be also always 1 or 2. And similarly, this will be always 0 or 2. So then you see that this will have a proper labeling, and then again we can use Sperner's lemma to find a tiny triangle, and in the same manner we have the one-to allocation properly. So okay, I guess that's all I want to say, and thank you for your attention.